I'm here with AMD, where we're talking about accelerating AI innovation for high-performance PyTorch at AMD. My name, it's a little echoey, is Nordeng. Just kind of a brief intro, and I'll be talking with Rob Suderman as well. Just kind of start off and give kind of a real quick overview of kind of PyTorch at AMD. Just kind of give kind of some high-level points, and then go into a more deeper dive of kind of better inference cases. But overall, we support eager execution. We have greater than 60,000 Hugging Face models that we test nightly for regression through like PyTorch ROCm, making sure that everything always works and works seamlessly on our hardware. We provide a Torch compile backend, which includes working with Torch Inductor along with Triton for large customers that we are working with in production. We include custom PyTorch op integration and implement them through like our Erie backend for target backends, IR, or different Pythonic kernel languages. And then we also provide multiple paths for AOT export when compiling one or more NN modules through PyTorch to compile deployable ready artifacts. And we have paths that go through MI graphics or Erie compiler flows. And what we're going to talk more in depth with is kind of the Shark ecosystem. And what is Shark? It's basically a collection of tools to enable AI workloads at high level. It's open source first. Everything is out on GitHub. Anyone has access and can download, get set up and run with it through our ML inference platforms. It provides front-end support for a number of different ML libraries. PyTorch, obviously, it's one of the major ML libraries out there, so we obviously want to provide support for that. And it does include support for Onyx, JAX, TensorFlow, or TF-Lite as well. And it's basically backend agnostic. You can compile down to different HIP ROCm backends, run CUDA, Vulkan, AIE engines, CPU, or VM. It also enables high-performance profiling and benchmarking to identify bottlenecks and reduce those to really eke out as much performance on your hardware as possible. And it's integrated with the closest to metal runtime software. And really, ultimately, it's built off of Erie as the back end. Erie is a end-to-end MLIR-based compiler. It provides full ML graph optimizations. It provides kernel generation, so you don't have, as developers, develop specific kernels for every hardware. You can automatically code gen those at our compile time. And then we can optimize for fusions and code vectorizations throughout the graph. It's front-end agnostic. We basically have various paths to go from your front-end, like PyTorch, to linalg, which is the actual input for Erie. And it contains a variety of different ML compiler runtime analyses to run your ML efficiently. And it does provide methods for compiling it down to shippable deployment artifacts, so you know exactly what kind of inference stages that you're looking at. So you're definitely going to guarantee whatever throughput you compiled it for, you're going to be able to expect that on your hardware. And it falls under the Linux Foundation AI and Data project, but AMD is essentially the largest contributor to it. And it is all built off of MLIR. It's a one central IR format, interfaces directly with PyTorch via Torch MLIR, and it falls under the LLVM Foundation. And down here at the bottom, you can kind of see just kind of an example snippet of one MLIR command, where you basically have your input, gets whatever your operation is. Could be anything from a Torch matmul to scaled out product extension or anything like that. And then you have your input, or multiple inputs, custom attributes for if you want to specify any specific tiling or hardware specific compiler flows that you want to go through. And it also provides custom types. Now, how do you go from PyTorch to our silicon? Shark provides that tooling, where we basically connect your PyTorch programs to run on Erie. A lot of Shark is kind of packaged up in what we call Erie Turbine. And what that is basically packaging Torch, Torch Dynamo, and various methods to capture PyTorch programs, including tools to provide Torch compiled backends that go through Erie and Torch export, where we can export Torch IR that we take through the various lowerings through Erie. And then Erie provides the full compiler and runtime necessary to actually generate and execute these on all of our hardware. You can kind of see on the overall flow here where Erie Turbine depends on Dynamo, traces that Torch NN module, generates that graph IR. Torch MLIR brings that down to linalg, and then we compile down to essentially any of our hardware. And we're able to execute anything from CPU, GPU, AIE, engines, NPU offloads, and all of that. Just go a little more in depth with what Erie Turbine provides within all its tooling framework is it has an AOT export method, essentially 3 different main things that it provides. AOT essentially is our more performant method. There's a little bit more work involved to get that working, but you're able to compile down 1 or more NN modules for your compiled VMFBs format that we actually run it. What it is basically just a one-shot tracing, as well as more advanced APIs to access all the full runtime features, including anything from dynamic shapes, mutable tensors or buffers, and external parameter management. We also provide eager execution through a Torch compile backend that works through Erie as well, and that enables turbine tensor device availability for interactive PyTorch sessions. And then we also provide custom ops support to integrate with defining custom PyTorch ops and implement them directly through Erie's backend IR or Pythonic language. All right, so now what we're going to kind of do is go do a little more in-depth of exactly how those advanced APIs to eke as much performance out as possible that you can. We're kind of going to go through an example of using UNet, which is one single model from SDXL's pipeline. It is the most computationally expensive and kind of takes up most of the inference time for a text-to-image type pipeline. So basically, you start off with you have your basic inputs for bringing in Torch and then diffusers. This is just kind of an example going through a Hugging Face model to run. And then Shark Turbine.AOT brings in all our Erie Turbine tools to connect basically Torch through to Erie. And then Erie for the actual compiler and runtime. But to start off with, you basically just instantiate your class that takes in an NN module. In this case, we're pulling from Hugging Face's Stability AI SDXL model. And then just your basic forward function, taking your inputs, providing that to that NN module. From there, you basically just instantiate that class from above, generate your input types. Here, we're just doing a Torch float 16 type inference. And this is just using batch size 1 just as an example. These could be dynamically shaped as well. And then we have, through Shark Turbine, the FX program builder for multiple entry points and a compiled module. Basically, behind the scenes, what this uses is Torch Dynamo to do one-shot tracing, generate the Torch IR graph, and export that. And this is just kind of the APIs to do so. And then from there, you export the Torch IR and compile it. This compile module will get MLIR module. Essentially what that's doing is just getting that Torch IR, as I was saying. For now, we have a big giant list of rocking flags because this example we're compiling down to MI300, and these are currently the large number of flags for best performance optimization. We are working to generalize those and bring those to all our different backends. But there are a couple specific, like our target backend is ROCm and targeting GFX 942, which is MI300X. And then from there, you target your ROCm backend, Torch input, that goes to Torch MLIR, lowers that down to linalg, and then we're able to compile that down and write that out to a compiled binary, which is that VMFB at the end there. And then once we have the export and saved to that VMFB format, we can load and run that for a runtime. The runtime is very minimal, very small. Once you have everything compiled down, you're able to basically execute that using a very small package. And as I mentioned before, you're going to know the characteristics of your runtime after you get that compiled. But yeah, going through this route, we've been able to achieve more than a 2 times latency improvement over naive, eager mode, and able to achieve really good performance on that. And like I said, we can run this across effectively all of AMD's hardware. There's also a C API, Erie Run module, that you're able to also execute these on instead of through this Python language here. Next, we're kind of talk about that profiling that I mentioned, which is kind of done through Erie Benchmark module, which gives kind of overall high-level ideas of that. But we also have Erie working directly with Tracy Profiler, which really helps us understand where all the bottlenecks are, where model performance workloads really could use more focus on. Overall latencies can really be pretty ambiguous, and it's hard sometimes to tell exactly where your bottlenecks are, whether it's specific kernels, could be just too many dispatches, creating too many kernel offload, kernel launch overheads, which this is all visible through the tracer that we have. Erie's built-in performance tracing, it dumps it on a per dispatch level, and dispatches are basically very similar to your kernels that have been basically code gen through Erie. Inspecting these can yield a very wide field of potential model and kernel improvements, anything from dispatch removal, potential fusion, horizontal or vertical across the entire graph, cases of missed fast points or fast paths. If there's some shape that for some reason doesn't go through the fast path, you can kind of look in and address that. And everything being open source, it's all visible as to what exactly is going on under the hood there. And there's also power and latency throughput trade-offs that you can kind of take into effect if your throughput is, memory bound, computationally bound, or power limited, or things like that. And this is kind of a visual of what Tracy looks like when you're doing your benchmarking. This here is just a very zoomed in portion of that UNet model. You can see basically all the different kernel dispatches mentioned here. It provides all the different shape inference of what's actually happening here. And what's highlighted here is just like an element-wise of some specific shape. You can see the gaps between kernels for your launch overhead, get an idea of where things, how long each individual kernel lasts, the time in between kernels for dispatches. And you can also see like missed fusion opportunities. Like potentially, maybe there's a way you could fuse this matrix multiplication with this element-wise and reduce the overall time on that. And then it also provides very more in-depth statistics for each kernel dispatch. You can kind of see all the different shapes for this here. Like for example, the top talking dispatch is that matmul transpose B of that specific shape. It provides overall total time, total times that dispatch is called, and the mean time per call. So very powerful tool that we've used to kind of identify where bottlenecks are and how you can address them. So what are the upsides of this? It basically leverages PyTorch as a very powerful modeling language. It's heavily used by a very wide selection of people, and we're able to directly integrate with that very well through everything from Hugging Face repository. We've been able to integrate with Onyx models, where Torch MLIR has an extra path, kind of take Onyx to Torch MLIR, and then basically follow that exact same path through PyTorch models. Everything's architecturally agnostic. You can do the same source program across CPU, GPU, NPU. It's OS agnostic, running Windows, Linux. Through that Tracy benchmarking, we can triage performance on a per kernel breakdown, identify dispatches, possibilities for kernel fusions that have been missed, and really identify all cases of bottlenecks to address. And then from there, you have a saved compiled artifact with very known performance that you can can rely on. And then I'll let Rob cover kind of what we can do next.
So something unique about being a hardware vendor is we really have to meet our customers where they're at. While we can start with an inherent PyTorch program built within it, we often have to bring this down into something to run on hardware and squeeze out every piece of performance that happens. The fact is that while these accelerators often have a very heavy upfront cost, the operating cost ends up being even higher. And so anything that we can do to squeeze out performance, can squeeze out the ability to fully saturate, is something that our customers actually very much need. And if you actually follow the space for this, you can look at something like GGML, which is doing an incredible amount of work in basically quantized types and sub-byte quantized types. They're taking a lot of inspiration from things like JPEG compression to be able to do blocked and super blocked quantized weight matrices. Or we can take a look over at the VLLM, which is doing basically sparse KV caches in order to decrease the memory overhead. This becomes particularly important with something as large as Llama being, or not Llama 405B being 910 gigabytes, and the largest accelerators you're getting maybe having 250 gigs of VRAM. So even if you squeeze this thing down to 4-bit, the ability to squeeze your KV cache smaller means you might be able to run more people at the same time when serving these things in workloads. And if you start considering combining all of these combinations, stock PyTorch starts having a little bit of a problem of there's no way to represent this in base PyTorch. And so we have to have a way of actually saying, okay, well, we want to write our PyTorch program and then have bailouts in order to inject things that are high performance that aren't well representable with an A10. And more importantly, aren't pure custom ops. We simply don't have the manpower, and I think no one does, to do every combination of every bit type, sparsity analysis, or technique for doing this. And so what we've basically leaned more into is essentially having this bailout mechanism via Erie Turbine, so that while we trace the program, if you're doing a trace via Erie Turbine and you hit a specialized operation, we can inject specialized IR specifically for this case. One of the standard examples with this is scaled dot product attention. I mean, we have C Flash attention version 3 came out this year. A lot of work is required in order to support this, not just at the outside level, but within in a similar way as flux attention. Without having that ability to control the inner loop, you can't necessarily perform the inner component of flash attention and re-quantize it correctly, use FPA. And we're also seeing this for sharded versions. It's reasonably large that even at, again, a 910 gigabyte matrix, you're going to have to likely split this thing across multiple pieces of hardware. And if you're doing, say, FP8 or I4 attention, you're going to be having to either program a combination of these or have a bailout mechanism that can work in tandem so that you're not having to handwrite each of these kernels separately. And even beyond that, the last thing of an automated compiler system, there might be the need to squeeze out that extra 2% out of a particular kernel. And if someone wants to sit down and write a Triton kernel and inject it in, they need to have an easy mechanism to do that. Otherwise, they're going to lose performance that they would otherwise gain, which is ultimately what our goal is to not have happen. So the main way we're demonstrating this right now is something called Shark Tank. It's basically a repository of state-of-the-art models leveraging Shark's full feature set. This can include sharding, quantization, subtypes, even parts built into our custom ops system, such that if you want to invoke your attention operation, you can know that you're going to be hitting the perfectly fused variant, and you're not going to have it somehow have some intermediate operation that means that we miss, say, the indirection via gather. And the end result being that you can take the program, run it through PyTorch, validate everything's correct, then export it, compile it with the full Erie toolchain, and leverage basically the full performance of your hardware. This way you're not having to write one thing and validate it on another in serving, and that you know what you delivers correct results no matter what, with the highest performance that you can get. So the main way we do this is via a form of custom operations specialization. The premise behind this is that if you just purely limit to what the PyTorch operators are, you're going to run into problems, and this is why we see more operations like flex attention come about. You can go and write your kernel and customize it the way you need it, specify a generic version. In the case of the bottom left, if we want to be able to doing some sort of quantized map mall, we can just say, unbox the thing, perform the map mall, basically dequant and do it, and you'll get one result. but you can support it to be overridden so that if you know that you're doing, say, an I8, I8 matmul, or an I4, I4 matmul, we can custom inject that piece of IR. So this is a polyhedral math computation, and that it will work well with the compiler because it's a well-known piece of IR, and it'll be injected and potentially even fused. What's different about this versus a lot of other custom op systems is most are based on, here is your dispatch, I'm going to go invoke your dispatch. Whereas this could be, this is your dispatch in very well-constructed IR, and hey, after this, you had an invocation of an attention function, it stays within the source IR, and so it can immediately fuse with the surrounding components. You try to basically build something as close to the compiler as possible so that the compiler can then be leveraged to generate the best performing code possible. And it ends up looking something like this. Despite the fact that these are two separate matmul invocations, so this is just op.matmul, we can specify one to say, hey, I operate on sharded tensors. If you get a sharded tensor, here is how I dispatch and break up my sharding, and then I can invoke separate matmuls and then do the actual gather together at the end. And on the other end, I invoke the version that's, say, block scaled. So this is either an I8 or an I4 implementation that ends up handling all the quantized components. And so if I make my I4 and then I throw it inside of a sharded tensor, I now get both a sharded version of an I4 computation, all without having to run it through. And if each has a default PyTorch implementation that we've included, you can validate it entirely with just PyTorch eager execution, and then export to something that you can compile and dispatch and distribute to your actual production without having to worry about missing the fast path, or at least less likely to miss the fast path. So essentially what we're trying to do is find a way to say, like, hey, we're not limited by the base operators that exist in PyTorch, but we also still want to exist and operate within base PyTorch, so you're not having to validate on only the one piece of hardware that that kernel is supported in. And by actually supporting out both custom kernel and composition, you don't actually lose any of these automatic features for doing things like tiling or data fusion for that operation. For anyone that's followed a lot more of the kernel space in this, things like data tiling layout is actually really important for performance, but you can't do that nearly as well on a single op standpoint. Because if you can have two ops back-to-back that both support data tiling, you can basically push the data tiling operation to the very outskirts of the program. And this can only really be done by having a full program optimization and being able to inject that exact piece of code in a way that is compatible. But that being said, it's also important that we have hand bailouts to existing both Triton or other kernel metaprogramming mechanisms. If someone really needs to get every piece of performance on a particular chip, we actually go right directly as being able to inject assembly code. So we work with the Tensile team to actually integrate some of their high-performance matmuls for low-bit quantization to actually see both in comparison of that to our existing code generation technique and help inform where we were in comparison to like a lot of the other work that people had contributed throughout the company. And the end goal being is that you don't sort of have to choose between what is like good and what is bad for performance. You can kind of get every single benefit as kind of mashed together as best as you can make it. The end result being that you can do something as follows. You can basically end up saying, I want to override this operation, specify and select a variant off of it. You can specify specialization. So you can say, I'm okay with a dynamic batch dimension, so I don't know what my batch size will be. It's particularly useful for sequence length for LLMs. But I do want to like specialize on, say, the inner product area because tiling actually benefits from knowing that it's block size 16. It makes a significant improvement to it. And then when tracing the program, it will inject every variant required prior to export so that you will only generate the minimal number of kernels required at compile time. And you can specialize for high performance. And the final piece is actually generating the kernel itself. So basically, it takes all those pre-canned alphabets, pulls a standard IR file. So for anyone who's actually written any of MLIR before, it's a basically single assigned language. And then you can inject that directly in as an invoked function. So essentially, it sidelines it and then has an invocation into that piece of custom code. In the case of, say, direct Haskell, which is like the actual assembly language, we can even directly say, oh, here, insert this dispatch. This is the exact dispatch you want to do, and it will just inline in with the existing compiler stack. So if there is an exact piece of assembly you want to invoke into it, whether this is coming from Triton or Turbine kernels or a lot of other projects that are sort of working in generating these high performance kernels, you can just integrate it in. It appears in your compiled binary and is shippable with no dependencies. So why are we doing all of this? The reality is that like PyTorch has had an amazing impact on being able to accelerate research, and we're seeing that it's continuing to go faster and faster. And the consequence of this is that n-squared matrix of combinations of features is getting really big. And it's not sustainable to have us writing every combination of features imaginable. I don't want to be that person sitting and having to write a sparse attention I4 blocked with some sparse matrices that isn't necessarily going to have anything more than the one application, when this is really a combination of existing features. By being able to write a way that we can actually inject IR, we're able to actually go and allow research to still iterate at that fast pace and keep up with it. And moving towards these sort of compiler-based solutions has meant that we've been able to actually much better keep up with current research. One of our sort of claims to fame by one of the individuals who sort of heads this project is the fact it took less than 24 hours to implement a flash attention 2 kernel after it came out and hit basically near peak throughput on, I forget what piece of hardware it was last year. And that we really couldn't have done this without a lot of the tools inside of Shark, especially on profiling and being able to do custom kernel injection. And this leads to the end goal, which is if you buy a piece of hardware, it's kind of useless unless you can get its full utilization. And the only way you're going to do that is more than just actually being able to write the high-level PyTorch, but identify high-performance optimizations like sparsity or quantization, and being able to make sure it's reusable across model architectures. Writing a pipeline for one LLM and then having to rewrite it for another just because it changes the attention layer or it ends up introducing like mixture of experts, and having to completely rewrite the pipeline is obviously not sustainable. And we're hoping that by building a lot of these tools, we're able to actually improve that process so that when you buy one of our pieces of hardware out of the box, you can get that high performance. Something that's worth even reiterating on this is because these pieces of kernel, like these kernels that we're injecting, are not hardware specific. In most cases, these are generalized polyhedral math. We're able to compile them and go for like auto-tuning, not just on CPU, but on GPU and NPU. So feel free to reach out to us, but one of our real hopes with this is that we can start having a real fast path to take existing LLM infrastructure and be able to ship a large number of the features that we're seeing in research on essentially all pieces of our hardware. So obvious disclaimer that this is still a lot of work in progress and there's a lot to be done, but we're continuing to see significant performance improvements. And we're seeing that really the next couple of years are going to require full-level model optimization. That's just the fact that we're really having to push this hardware a lot harder than we ever realized, to the point that even being able to disable like a chip on a card may make a difference from either how much power it pulls or how much heat it generates. And we're hoping we can continue to improve that level of efficiency, especially within inference workloads. So thank you for your time. If you have any questions, feel free to find myself or Ian and ask any questions. But I'm already running a bit tight, so thank you for your time.